Hey, welcome everyone. My name is Paul Deffenbaugh. I'm the editorial director at Metal Architecture Magazine. I'm glad you joined us for today's webinar, which is on FEVE architectural coatings, high performance coatings for expansive, sustainable design. Today's webinar is being presented by Lumiflon, and it is part of the Metal Architecture webinar series. I'm going to turn things over to our speaker, Kristen Blankenship, in a moment, but I wanted to let you know how we're going to proceed. Kristen has a lot of material that she's going to go through, so we're going to hold questions till the end, and then she will respond to all of your questions. You can submit questions on the panel on the screen on your window there. If you don't get your question answered, we don't have time. Tomorrow, you're going to get a follow-up email. It will provide a link to a video of this webinar that is going to appear on our website by Monday morning. You can watch it there again. And that email will also have contact information so you can get more information and ask technical questions. For those of you who need AIA credits or certificates, those are going to be handled automatically. Please allow 7 to 10 business days for everything to process. Now I'm going to like to introduce Kristen Blankenship. Kristen is the Business Development Manager at AGC Incorporated Lumiflon. She has a Bachelor of Science degree in chemistry from the University of Evansville. She spent the last 19 years in the coatings industry working for various coating, chemical, and material manufacturing companies. Kristen began her career as an analytical chemist at Red Spot Paint, focusing on defect analysis. And that experience allowed her to develop a unique approach to formulation with a focus on structure-property relationships. She eventually became a UV curable coatings formulator at Red Spot and later moved up to Cytec Industries as a technical service chemist. In 2013, Kristen became technical service chemist at AGC Chemicals Americas, and after 3 years working in the lab, she moved into business development. She now supports strategic accounts in developing high-performance coating technology based on Lumiflon FEVE resins. Kristen, you know what you're talking about. Take it away.
Thank you very much, Paul. Thank you, everyone, for joining today. I think it's afternoon and still morning in some parts of the country, and for my colleagues over in Japan, if you're listening, you're not getting any sleep tonight. So thank you, everyone, for joining again, and we're going to kind of hop right into this. So this is about FEVE architectural coatings, high-performance coatings for expansive, sustainable design. And if you're familiar at all with AIA-type presentations, there's a little bit that I need to go through first. So bear with me as I read through these slides. AGC Inc is a registered provider with the American Institute of Architects Continuing Education System. Credits earned on completion of this program will be reported to AIA CES for AIA members. Certificates of completion for both AIA members and non-AIA members are available upon request. This program is registered with AIA CES for continuing professional education. As such, it does not include content that may be deemed or construed to be an approval or endorsement by the AIA or AGC Inc of any material of construction or any method or manner of handling, using, distributing, or dealing in any material or product. And as Paul mentioned, we will review questions at the end. And this is live. It'll be a 1-hour course, and you will receive 1 AIA CEU. And you can see here where you can send your information to get those credits. The course description here: in this 1-hour course, we will discover the strengths and advantages of FEVE fluoropolymer top coats. We will evaluate coating performance tests, including accelerated weathering and real-time weathering, and what the implications are for the life of different coating systems. We will explore the many possibilities that FEVE technology provides and assess the sustainability benefits of FEVE top coats, despite their higher initial cost compared to other top coat formulations. The course objectives here: by completing this course, the design professional will be able to define FEVE coating technology, history, and unique weatherability properties, as well as its ease of application in the architectural market. discuss the importance of the form of coatings, including color, finish, and gloss range, discover the function of a fluoropolymer coating in terms of performance, substrates, and types, and finally to describe the sustainability and environmental impact of long-life coatings. So we're actually going to start with the function of fluoropolymer coatings. So just to kind of conceptually think about paint, I would say the only people that really care much about paint are those that actually make it. Even people that use it, I don't know how much they really like it. It serves a function, and that function sometimes is just aesthetics, but oftentimes it's to protect the underlying substrate. And when you're thinking about performance and a substrate that needs a lot of performance, or an application, infrastructure, asset, whatever you want to call it, where that coating is going to be applied, that's where, you know, like a steel bridge or a curtain wall for a high-rise building, that's where performance really matters. And so these types of coatings, specifically fluoropolymer coatings, are really high-performance coating systems. And so when you're considering what type of paint you actually need, we are talking about chemistry. And that chemistry can do different things. It can help with mechanical strength. It can help with resistance to sunlight and exterior weatherability. It can help kind of give you a balance of properties, toughness along with chip resistance or durability. And finally, it can protect against corrosion resistance for sensitive metals. And in the class of fluoropolymer coatings, there's really two primary types that kind of hold the market right now, and that would be PVDF, or polyvinylidene fluoride. This type of material is a thermoplastic fluoropolymer. There are some iterations of it that have come out in the last few years that I do believe can be cross-linked, but primarily when you think of the spray liquid coating extrusion market, you're thinking
Kristen, I think we just lost your audio. Kristen? Give us a second, folks, while we sort this out.
just one moment.
Thank you.
I think I'm back now.
You are here.
Okay, good. All right, we'll keep moving. So as far as how this type of material is used, it's usually in a blend with an acrylic resin or other resin. Again, you know, I'm not in the business of PVDF, but it is in this market space, so this is kind of just the general market information. The key thing, of course, though, with this type of material is that it withstands UV exposure for, you know, 2, 3, if not longer, over the course of the life cycle of the asset. The other type of fluoropolymer system, which we'll be spending most of our time reviewing today, is FEVE. And there's many ways that people pronounce this. So if you're thinking, what is FEVE? I thought I was listening to the FEVE webinar. Well, that's because a lot of people call it FEVE, but I've heard FEVE, FEVE. So as not to offend anyone, I just stick with FEVE. FEVE is an acronym for a tricky sounding chemical. It's called fluoroethylene vinyl ether. And of course, that chemistry or that chemical name may sound a little bit scary to some, but don't worry, this is a long chain fluoropolymer. It's not the ether that, if you're my age or older, you may have actually used in the organic chemistry lab in college. I doubt they let that ether be used now. But in any case, this type of fluoropolymer is a little bit different than PVDF. We'll talk about the differences. One is that most of the FEVE fluoropolymers used in the market are thermoset or they are cross-linked. So that kind of is one difference. Where they do find similarity is in performance, and that really is because they both share that fluorine. That carbon-fluorine bond is what is so critical to the performance of all fluoropolymer systems, especially when it comes to weathering. The carbon-fluorine bond is very strong. The energy of that bond is higher than the rays of, well, the majority of the rays of UV light. And so that chemistry just doesn't break down when exposed to UV light. So that's really where the performance comes in. And you can see here with FEVE, you'll have weathering resistance for 2 to 3 times longer, again, than a conventional coating system. Another difference with this type of material is that, again, this is compared to the traditional solvent-based spray-applied PVDF, is that it can be applied at room temperature, it can be applied in the field, it doesn't need ovens to cure, and that really has to do with the chemistry. So we'll spend one slide on the chemistry, so bear with me. One thing you might notice right away is the color, and you've got blue spheres and green spheres, and they're alternating. And that is actually a fairly accurate representation of the alternating structure of this material. We call it a copolymer. So this is not inherently a blend. This resin can be blended with other materials. So when you think of PVDF and you might spec in a 70-30 PVDF system, you're not going to see that kind of language typically with an FEVE system because they're often not used in blends, but they could be used in blends. So that's just important to keep in mind. The material is a copolymer. It's a unique alternating copolymer structure, and that alternating structure is what gives it its performance. Vinyl ether alone does not withstand weathering. If you know anything about PVC, you know that it chalks and degrades unless it's properly protected, either whether it be light stabilizers and the plastic composite or a coating on top of it. But when you have these fluoroethylene units next to it and in this perfectly alternating structure, that's where you get protection of those vinyl ether bonds. Why do we have vinyl ether in it if it doesn't weather? Well, you have vinyl ether so that you can be very soluble in many different common solvents, and so that you have basically an amorphous or non-crystalline polymer that can easily form a film at room temperature. So no heat is actually required to form these films. That does not assume that heat can't be used. It certainly can. It's just that it's not a prerequisite to use these materials. And so when they first came on the market, that's really the market area that they were used in, were those field applied applications. As far as the characteristics, you can see, of course, outstanding UV protection, excellent gloss, color retention, and chalk resistance, good adhesion directly to metal. This is another characteristic that is a little bit unique to the fluoropolymer space. You can actually apply an FEVE coating directly to metal, and a primer is not necessary. Of course, it depends on the application environment and the service environment. If it's a highly corrosive environment, then the paint manufacturer may recommend a primer for that extra protection. But it's important to note that this kind of will allow you some design flexibility. And of course, that's the second part of this webinar, so we'll save it for then. So again, shop or field application, these materials actually cross-link in a way similar to a standard polyurethane system. And so standard painting equipment and application can be used. And I always say that I would be very surprised to find any painter or contractor that could open up a bucket of an FEVE paint and know that it was different than a standard polyurethane. The materials are very resistant to cleaning solvents. Again, that's the carbon-fluorine bond, and that can be helpful if you need a graffiti-resistant coating. And where it really comes into play, because this is something that, there's a lot of fluoropolymers used in the world for a lot of different materials. So some people think fluoropolymers, they think low surface of it or energy coefficient of energy, and of course that means that can I even paint over it? These materials aren't quite like a pure or true fluoropolymer from that standpoint, so their surface energy isn't super low. So you can still graffiti onto the coating, but what will happen is if you need to clean that or remove that graffiti, whether it be paint, spray paint, or Sharpie, or what have you, you can use those harsh cleaners that you would need to remove the graffiti agent completely without damaging the top coat with the FEVE in it. And so that's really the key, because a lot of times when you're removing graffiti, if the coating system it doesn't have enough integrity and resistance to the cleaning chemical, you get kind of a grayish or shadowy effect. And so even though the graffiti's gone, you still have this obvious difference between the finish beneath the graffiti and next to it. And so with an FEVE system, in that way, it can be considered anti-graffiti. The other thing to note is that FEVE molecule that we showed you previously is really the backbone polymer that will be used in all different versions of FEVE resin grades. And so there are versions that are water-based, there are powder grades, and the water and the powder grades definitely can help meet some of the very strict air quality regulations in different parts of the country and the world. The benefits, one specific benefit to the architectural market would be that these types of systems can meet the AMA 2605 standard. Of course, that's 10 years after South Florida with greater than 50% gloss retention. Excellent weatherability, of course, mar and scratch resistance, and that really comes from the fact that these materials are cross-linked. Corrosion resistance as well. So while I mentioned before that you can use FEVE directly to metal, it'll stick. But if you're in a very highly corrosive environment, you might want a primer. So you may be thinking, well, how are these corrosion resistant? Well, corrosion resistance, when you think of, say, a steel bridge and you think of typical paint systems, you think of a zinc-rich primer, some kind of mid-coat, probably an epoxy mid-coat, and then some kind of top coat. Could be an acrylic, could be a urethane, could be a polysiloxane, could be an FEVE system. But all that being said is the anti-corrosive activity really comes from that zinc-rich primer. What the FEVE top coat will do is it'll act as a very strong barrier to those corrosion initiators. And of course, that's moisture and salt. And it will also maintain that barrier performance much longer because it's not degrading in the sunlight. So when we talk about corrosion resistance, that's what we're talking about, barrier properties. I keep talking a lot about that these are thermoset or cross-linkable, but there are grades that do not need to be cross-linked. So they could be used in thermoplastic systems as well. Primer, again, optional, depends on the service life environment. They're ideal for curtain walls, facades, bridges, and useful for both new construction and repainting. So the next few slides, we're going to review a little bit of the weathering and kind of give you an insight as to what paint formulators look at on a daily basis, especially when they're in the business of highly weatherable coatings. Look at charts of weathering. And here you have a chart where you're looking at, on the x-axis, you're looking at hours of exposure, and on the y, you're looking at percent gloss retention. And I'm going to explain a little bit on this slide about weathering in general, and then we're going to kind of zip through the next few. But I think it's important to explain why, when we think about a coating and how it withstands weathering, sometimes we look at its gloss. I think sometimes, especially in a lot of the architectural space, most of the coatings are not high gloss. They're actually more of a satin. You know, some coil coating applications, you will, signage, think of signage, you might have really high gloss, but for the most part, architectural coatings aren't very reflective, and that's good, because if you think about a 60-story tower, if the sun is hitting that and then hitting the pavement below, that's not the greatest thing if that coating is very, very reflective. So most architectural systems are not high gloss, but that being said, gloss is not just an aesthetic characteristic. It actually is a characteristic that indicates film integrity, because the process of photochemical degradation actually starts with UV light actually cleaving weak bonds in a polymer backbone. And as it starts cleaving those bonds, you start actually getting changes and movement in the mass or bulk polymer. And that can start to cause cracking and voids, and ultimately will allow for the infiltration of water and salts that then further degrade that coating system. And you end up actually with erosion over time, where the coating, it just turns into particulates and it gets washed away. So you may start with 3 mils and then you're down to 2 after so many years. So again, gloss retention is really an indication of film integrity. So if you're losing gloss, you're having chemical changes in your coating, and it's usually because the weathering has started to occur. And so when we look at these graphs of accelerated weathering, we're looking at the change over time. And you can see here with the FEV system, very little change after 5,000 hours with QUVB. So that's actually a very small portion of sunlight, but it's very, very strong energy, and it really rips apart almost all organic bonds except the carbon-fluorine bond. And that's why if you have a fluoropolymer, you're likely going to do well in this test. But it just gives you a relative indication of how these coating systems stack up. If we go here, we look at sunshine weatherometer, a little different test, same concept. These are chamber tests where you put panels in a box basically, and then you have a bulb with different types of irradiance, and then you just let them sit and you measure the change over time. And here you can see both the FEVE and the PVDF system do very well after 4,000 hours compared to that conventional acrylic urethane system. Another test that's considered an accelerated test is xenon arc. You can see that on the left. Xenon arc, actually, the bulbs that are typically used mimic sunlight very, very well. So some people feel that if you get the moisture component right, that xenon arc can really mimic sun exposure in a decent way. I'm not going to go out on a limb and say very good, but pretty well. And then the Amaqua test you can see on the right. That's actually a trade name. There's another trade name called Q-Track from a different company, but both tests are really hybrid tests between accelerated weathering and natural weathering. You put the panels outside, but you actually use mirrors to take the sunlight and intensify it onto the panel. And so if you can imagine a jig, basically, where you have panels on one end and then 180 degrees from those panels is a set of mirrors. And those mirrors are all tilted at different angles, and they track the sun as it goes across the horizon. So you're always having that intensity of light. So really, you're getting natural exposure, but much more quickly. So Amaqua and Q-Track are both tests that can kind of give you a little better indication of what's going on in your system. Of course, real-time weathering is the best. It gives you the most realistic results. But if you're talking about a long life coating that could last 10, 20, 30, 50, 60 years, then you have to wait 10, 20, 30, 50, 60 years. And of course, time is money. So what the industry really does with these high performance coatings is they get systems out on the test fence. We always say get them on the fence, or get them on the rack. So you get them outside and you start watching them. In the meantime, you use the accelerated testing to compare and contrast. There, unfortunately, to date, really is no accelerated test that really, truly matches what South Florida will do. Some are very close, and then what will happen is, like a xenon arc will get really close, but maybe in a certain color space or a certain chemistry, there's a lack of correlation. So it's really hard to get universal correlation across all paint chemistries and all paint colors. So for now, what we do, like I said, is we get those first formulations out on test fence, and then we start doing the actual formulating work using the accelerated test compared to what we put out on the fence as kind of a guide or a control. But anyway, so you can see here with the South Florida testing, if you look north of the line, that would be the unexposed area. So that's the area that's basically a control. It's covered. And south of that is what's exposed. So you can see in that red coating on the left, you have an FEVE after 10 years, very little to no change. Whereas with the high performance polyester, after 3 years, you see quite a significant change. On the right, you see a yellow color comparing both the fluoropolymer systems, very little change after 10 years. And in the middle, we have a dark color. Dark colors are important to note that up until probably a few years ago, a black coating, for example, is going to basically generate a lot of heat. It's not reflective. So the sun, you all know that. And so some coating systems and chemistries are actually sensitive to both UV light and heat degradation. And so you can kind of see that here with the polyester versus the two fluoropolymer systems. Fluoropolymers are also relatively more heat resistant than their conventional counterparts. I will tell you that today, I believe a lot of paint companies are using infrared type dark pigments, and those are pigments that actually reflect the heat component of UV light, and that can be very helpful to maintaining good performance over time. And then another way of looking at Florida testing is graphically, and so you can see here after 10 years with these two systems based on FEVE gloss retention of greater than 60%, which of course passes the AMA 2605 standard. And then here you have some Okinawa weathering. Okinawa is very similar to South Florida. There are a few differences. The test site for Okinawa is a little bit closer to the coast, so the corrosion may be a little bit higher. And I believe, I can't remember off the top of my head, but I think the heat might be a little bit higher. So you can see there, 80% gloss retention after 12 years. So in some ways, this could be a more intense test than Florida, depending on if it's a clear or pigmented. And that's another thing to point out, is that a fluoropolymer coating performs very well. When you put it in a formulation, you have to be careful of the other things that go in it. So you can see here we had 80% gloss retention after 12 years, and the other formula was 60 after 10. So formulation does matter, but generally speaking, a fluoropolymer system is going to weather very, very well compared to a conventional counterpart. Here's an example of offshore marine testing station. So this is where you actually have a coating or a rack out in the middle of the ocean. So you have all of it. You have sun, you have wind, you have salty air, and this is actually graphical representation of chalking. So there's actually an ASTM method for chalking. It's really, really technically difficult. Just kidding. You take a cloth and you wipe the surface gently, and you look at the cloth and you see if there's any residue on the cloth or any pigment. And as we talked about earlier with photochemical degradation, what happens? You actually start losing film integrity. So if your resin system starts degrading and those pigments, which are just loose pigment, right? We've all seen pigment loose in a bag. If it's not held together by the quote glue of the resin, then it's just going to come off and you'll get it on the cloth. So they have a rating system. 10 is the best, and of course as you go down it is increasingly worse. So you can see here after about 10 years that polyurethane is completely chalked. So the FEVE goes to 20 years without hardly any chalking at all. So we'll talk just briefly on corrosion resistance. I'm running up against the clock here. With corrosion resistance, again, it's the barrier properties. One way of testing that is electrochemical impedance spectroscopy. That's where you run a current through the film. Most organic systems are going to be insulating. They're not going to allow a current to go through. Of course, if you start having those cracks and voids, then you're going to allow salt water to come in, and then of course you can get a current through. And so that's what you're seeing here. Whereas the FEVE maintains the barrier, remains more insulating, the other systems are starting to degrade, and therefore they have less impedance. And the next few slides just kind of show another representation of that using a chamber test. And here's a salt fog test, and you're just looking at corrosion coming out of the scribe. And really the point here is you're looking at a comparison of what are traditionally considered very weatherable and very durable and corrosion resistant systems that are used currently on steel structures like bridges. And you can see that the FEVE top coat compares very well, in some instances maybe slightly better. So now we're going to move into the different types of FEVE, what we call resins or binders. So there are solvent-based, much like we talked about traditional PVDF. There's also resins for low VOC and HAPS-free systems. So these are actually flakes. So they're a solid resin, but the idea is that you can then dissolve them into whatever solvent you would like. And that would include what are called exempt solvents or low VOC solvents. So you can have a solvent-based coating that's actually low VOC. And these are used a lot in industrial maintenance applications. Think of water tanks, where in certain parts of the country you need to have VOC less than 100 grams per liter. And it's difficult to do that in a solvent-based system, but in the US we can use what are called exempt solvents. I don't foresee that being something that we can do indefinitely. There are some regulations that have already been implemented and are going to continue to be implemented where the exempt solvents that are remaining are going to be probably none at some point, and the market will then probably have to move to water-based. We do have water-based systems, and then finally our powder coating resins. Solvent-based is really the traditional form, and I've always wondered what people that are outside of the coding or chemical industry must think of the people that are practitioners of it. Because all you hear about when you hear, chemicals are bad and solvents are horrible and toxic and all of these things. And so you might be wondering, why were they ever used in the first place? And it's because they worked. Xylene is a powerful solvent and dissolves many, many things. And when you're talking about a coating and applying a coating and allowing it to flow and level nicely and give you a nice smooth finish, being able to dissolve these organic polymers very, very well in a very strong solvent can allow you to do that. And so that's what was done. It wasn't until these materials were studied after they were in use that the realization hit that they were either harmful to the environment and or to human health. And so now the regulations are in place and there are limitations on it. They are still used today. If you think of the coil coating process, they are used there. They use thermal oxidizers to convert the VOC into CO2. Of course, that's CO2, so that area is being looked at. Overall, the coil coating process is a fairly energy efficient system, but of course there is some eyes on that process. But for the most part, it's still being used. And so there's still quite a market share for solvent-based liquid coatings when they're used as safely as possible. There are resins for low VOC and HAPS-free. Again, I mentioned those, the solid flake resins that can be dissolved in VOC-exempt solvents. Water-based, of course, these are a low VOC option. I will tell you, most of the time there is some organic solvent in a water-based coating, and I think it speaks to a larger issue. If I were a layperson and not in the paint industry, I'd be scratching my head, well, why isn't every paint water-based? And every paint is not water-based because organic polymers are basically oil. They're oily. And you know what happens when you put oil in water. It doesn't work very well. So water-based coatings are very different animals than a solvent-based system. And over the years, I will tell you, the coatings industry has made leaps and bounds on this technology. There's still more work to be done. We are doing the work ourselves with the water-based FEVE systems we have, and we think that they provide the same performance or similar performance to the solvent-based systems. And as the regulations continue to come down the pike, they're going to be looked at more and more, and they're going to be used more and more. So it's really just a technology innovation and continual study in the lab to see how to get these things to work well. So, if you're wondering about that, which I know I would be, that's why. We're just trying to help make these systems go together better and form good films that have good integrity. And then finally, powder coating resins. This is an area of growth that we're seeing. And, with powder, you have no VOC. You have no water. It's just a powder. So, in fact, in the powder coating industry, some people consider the solvent air. Well, air is still okay for the most part. Powder coatings do use ovens for cure, and of course that makes sense because they literally are powder particles, so they do have to melt flow onto the part to make a film. But needless to say, they are considered one of the most environmentally friendly options in the organic coating world today. So when we move on to the performance characteristics, the solvent-based systems, the liquid coatings, they can be used in curtain walls, they can be used in architectural components, factory applied onto aluminum coils to make ACM panels, spray applied on composites as well. And they offer the same performance characteristics as FEVE powder coatings, including superior gloss retention, resistant to chalking, and of course airborne chemicals like acid rain. When you move over to the application of an FEVE liquid system, this is where, again, the chemistry comes into play. FEVE is a non-crystalline material. It's amorphous. It flows at room temperature. You don't need, of course, the liquid. You don't need heat to form a film, so they can be used in field-applied systems. And here's an example of that, where you could have an epoxy or polyurethane primer coat applied prior to the FEVE top coat for most environments. Also could use a zinc-rich primer if you're in a corrosive environment. And then that FEVE top coat can be applied via a spray application, brush, or even roller. As far as factory application for an FEVE liquid coating, again, coil coatings and spray applied coatings can be used with these materials. So moving away from liquid onto powder. Powder coatings are used for OEM or factory applied aluminum extrusions. That's one pretty large application. There are others, but that's a significant area where they're used. These materials, just like the liquid version, can offer 30+ years life as a top coat with superior gloss, color, chalking resistance, and again, resistance to chemicals like acid rain. They are ideal for new construction. Again, these are applied in a factory, and so new construction tends to be where they are used. They do not have solvent or VOC, and so basically what's in the bucket goes on the wall. The application of powder utilizes electrostatic spray deposition. So that type of spray, along with the heat needed to make the powder flow, is why right now they're fairly limited to the factory or job shop. Of course, I'm sure there is some interest in innovating so that these could be applied in the field, but that needs to be developed. As far as substrates, these can be used on a wide array of substrates. They're used a lot on metals, including aluminum, steel, copper, and zinc. They can be used on fiberglass and other composites, porous substrates like concrete, fiber cement, wood, and also glass. So we talked a lot about the performance of these systems, and now we want to move on to the form. So the performance being the function, what do they do, why are they there, how do they protect substrates and assets, and here is what do they look like. And there is a section on this because FEVE can offer some expansive design compared to some other fluoropolymer systems, and that really goes back to that unique copolymer chemistry. They can offer the ability to use a wide range of crisp, clean colors, and so we'll get into some details on this in the next few slides. They can be used with bright, vivid pigments. They offer a wide range of gloss, from completely flat to matte to semi-gloss to high gloss, and they can be used in field touch-up paints to repair damaged areas. So the chemistry, again, it's non-crystalline, so it is basically amorphous, and it allows it to be inherently high gloss. So if you look at a flake of FEVE, it's basically clear and transparent and shiny. So this material, if you don't put any type of matting agent in it, will give you a very high gloss finish, and that is unique for fluoropolymers, and it's something that kind of sets it apart. If you need it for high gloss, if you need something that performs well in high gloss, FEVE can give you that. Another thing to consider is that if you're doing a metallic or a brighter color, when you think about something that maybe is slightly lower gloss, if you think PVDF traditionally, you think 20 to 40 gloss. The material itself is not completely transparent, and again, that has to do with the chemistry. So if you were to put a pink pigment, a bright pink pigment, into a clear glass of water versus into kind of a hazy or frosted glass of water, you would see a difference in that color. And it's really the same thing with the resin systems. So if you're doing something that needs to be a bright, vivid pigment that needs to pop, a more transparent resin system is going to help you achieve the look that you're going for. These are also used in metallic systems, whether it be the aluminum metallic or mica. They have good adhesion directly to metal, and so you could actually achieve a more, quote, natural metal look because you could actually just put a clear layer of an FEVE top coat directly to that metal substrate, and it would allow that natural metal to shine through. They can be used with special effect and, quote, functional pigments to give different looks, color shifting pigments. They can give a textured appearance. And then we talk a lot about how you can have high gloss with FEVE, but you can have low gloss too. So these can be used in matte finishes, and where they can really, they found their space is in field application of old PVDF. So up until recently, there wasn't an option for field applied PVDF. That has changed, but before that innovation, FEVE systems were there to kind of fill that gap. Bright pigments. So again, if you're putting a bright pigment into a clear, transparent matrix or resin system, it's going to allow that bright pigment to come through. And the nice thing about it is it's going to maintain its appearance for longer. And I love this image, this structure here, because it just illustrates so perfectly the utility of an FEVE system. Look at all the shades of that red. Some of those are organic. A lot of them, I think, are probably organic based. So they need to weather really well, because if they start fading, that color gradient that you see is going to go away. And what's going to happen is what right now looks like a very textured three-dimensional structure is just going to look flat. And so that's what I just think this structure really illustrates why an FEVE system would be used compared to something that's going to weather faster and it's basically going to allow those red pigments to degrade, and then you're not going to see that variation in color. That variation in color, again, is what gives you that three-dimensionality. So just in kind of summary here, FEVE can be used from anything that's matte to high gloss, can be used as special effect pigments, can be used in metallic systems, whether it's a metallic pigment or it's just a clear directly to metal to allow a metal look. And finally, it's a clear resin matrix that allows for the use of bright colors. So these days, it is very important to consider the environment. It always has been important, but we, of course, never really realized how important until the last 50, 60, 70 years, if you want to say. And of course, in the last 20 or 30, it's been forefront in most people's minds in most industries. And so we have just a few slides here on, what it means to have a long life coating and how that can contribute to sustainability. So a long life coating inherently is sustainable from the standpoint that it eliminates the use of more paint. So if you have a structure and you need it to last 60 years, if you use a conventional coating system, it's likely going to need to be repaired, repainted, 1, 2, maybe even 3 times. So what happens in a painting process? Well, you have to get the raw materials. Then you have to put those raw materials into a coating production process. You have to transport the paint to the job site. Before you apply the new paint, you have to prepare the substrate, which oftentimes is blasting off old paint. And then you have to collect that and you have to do something with it. Of course, when you're transporting paint to the job site, you're entering traffic. And then, of course, when you're leaving as well, there's also a traffic consideration if you're on an infrastructure project where you're having to block traffic so that you can, properly repaint, say, a bridge. And of course, that causes traffic delays and cars just sitting idle. And then of course, the paint itself may off-gas VOC. So every time you repaint, you have to redo this whole process. And so that impact to the environment just gets redone again and duplicated. With a long life coating, if you can eliminate 1, 2, or 3 of those repaints, you're actually much more sustainable. So we mentioned earlier the different types of FEVE resins. So in order to achieve a low VOC coating, you could utilize a low VOC solvent-based coating, again, based on the flake grade, utilizing an exempt solvent. You could use a water-based coating, and then, of course, you can use a powder coating. Powder coatings, as far as environmental performance, low VOCs, obviously. Most of these systems are going to be one coat. You can get really good performance in just one coat. Don't need a primer. Of course, it depends on the application environment, but for the most part, you can have that adhesion directly to the metal. Powder can be reclaimed and reused. It doesn't always make sense depending on the color. But it can be. And so the general average efficiency of a powder coating process tends to be higher when you think of transfer efficiency than its solvent-based counterpart. There's reduced energy use, and that really comes in because powders cure at a lower temperature than PVDF liquid coatings. It's still a high temperature, but when you're in the range of 400 degrees Fahrenheit versus 450 or 460 degrees Fahrenheit, the energy to power that oven up past 400 degrees is significant. I don't think it's quite linear. I could be wrong. But so there is a reduced energy use just from the cure temperature alone. There's reduced carbon dioxide emissions. Of course, there's no VOC in the paint itself, so that's one factor. But there are others. No hazardous waste, no hazardous disposal. And currently the EPA does recommend powder coatings as a sustainable coating option. There are non-chrome or non-toxic pretreatments available. Of course, you want to consult ALMA 2605 and the industry in general for guidance on that. And then, of course, because FEVE powder is rarely used with a primer, you know, if there are chrome-based primers being used, you don't need them anyway. So that's a benefit as well. And these can help with LEED credits, and we'll see a little more on that coming up. So on the LEED credit, the one that I think really stands out for me with powder is it's a little bit newer, I think, and it's this building product disclosure and optimization. I don't know that the credit is newer, but the ability to meet the credit has changed because the ACA has now created a product category rule for powder. So now you can actually get an EPD, and if you have an EPD, that can contribute to this building product disclosure and optimization credit. It's just having an EPD for your powder coating is not enough, from my understanding. You need EPDs for several of the materials on the job site, but this can contribute to that. So I think that's important. This can also help with building life cycle impact reduction, heat island reduction, minimum energy performance, and of course, heat island reduction in the innovation and design category. Just a little bit more on that. And then when you think about sustainability, long life coating, there's life cycle cost. Of course, nowadays, I think there's an appreciation for not just monetary cost, but also environmental cost. And so this is looking at just the monetary cost. And so you can see here that, yes, FEVE systems, fluoropolymer systems in general, they're high performance. They do tend to cost more. So those, you know, the sticker price, if you will, is higher. But because they last longer, they don't need to go through the repainting cycle. Their total applied cost ends up actually being quite low compared to the other traditional systems like a conventional polyurethane or even an alkyd system. There's also, when you think of again, there's monetary cost and there's the environmental cost. And so these days there's a lot of work being done with carbon footprint analysis, and our company decided to utilize a third party to do a carbon footprint analysis of basically liquid versus powder. And in the ALMA 2605 space, the comparison would be between FEVE powder and PVDF liquid. FEVE liquid just isn't used a lot in the spray extrusion process, so that's why it wasn't used. But I just kind of want to point that out. In the extrusion market for fluoropolymer in 2605, you really have FEVE powder and PVDF liquid. Of course, it's a generality. There's details that I may not be aware of, but just generally speaking, those are the two materials that kind of service the market. So we wanted to look at, you know, because powder does use an oven, you know, there's a concern that, you know, what kind of environmental benefit is really there? And so we wanted to do this analysis and look at it. And so you can see here in the chart, we not only looked at the cure temperature, which I mentioned before, and you can see that gradient there, but also the transfer efficiency. And so with reclaim versus not with reclaim, so that 90% is when you reclaim the powder and the 70% is when you don't. And that's versus 80 and 60 with the PVDF. And, you know, that can be debated, I'm sure, all day long. But generally, the transfer efficiency is going to be a little bit higher inherently on powder versus liquid. So if you move over, you can see here that generally speaking, an FEVE powder process it does have a lower carbon footprint. So even though you're using those ovens to cure, that solvent is just a big factor contributing to CO2. But also that slightly lower oven temperature does help. and then the transfer efficiency also. So overall, you are seeing a benefit there. So we wanted to kind of put some analysis behind what I think a lot of people have been thinking, but we wanted to put some numbers behind it. So now I'm going to kind of go through some case studies before I get into that, and I'm going to go through those fairly quickly because I do want to save time for questions. In specifying an FEVE coating, I will tell you we have a lot to learn. We are a resin manufacturer, and we sell a little bit differently than some of the other fluoropolymers in the market. So there's a little bit of a difference there. I would definitely urge you, if you have questions, if you're an architect, please call me. That's one of the things I've noticed is that just having this interaction with the market can be very helpful because I can connect dots sometimes with the paint companies themselves. So needless to say, there are specifications that an FEVE system will help you achieve, and they're listed here, not just architectural, but some military and even industrial. And generally speaking, when you're looking at a specification or you're going to specify an FEVE coating, these are some phrases that might be used. Again, it's not a complete list, but it's just to kind of give you an idea. When you're looking at an FEVE powder system or just an FEVE system in general, the one big thing is that it's often not calling out 70-30. So that's something to keep in mind. And then I've heard a little bit from the industry that a lot of specs call for liquid fluoropolymer 2605. And so that can be a little bit confusing maybe to the market because, you keep hearing about powder. Well, the specs calling for liquid. So there is some, education and outreach going on to help people understand that a powder coating that's specified for 2605 can probably meet that specification. So again, just something to kind of throw out there in just general terms to consider. So as far as projects, these are going to be liquid and powder. So just remember that we just got done talking about powder. So, but FEVE is in liquid systems and powder. So here we have an ACM panel application. This is the NASA laboratory in Virginia. This is an application in Australia, another ACM. You can see that high gloss. ACM again, HSBC Center in Australia. And here's where that bright color comes in. And you can imagine if those colors started to fade, it would just really be sad, I think, for the building. Here's an application where they're actually using a single skin aluminum instead of that traditional sandwiched ACM panel. And this is the Canopy by Hilton in Oregon. Here's a powder application, and this is one of the Hudson Yards towers. There's several towers there. FEVE is used on a few of those, the newer project. Here's a non-metal application. This is fiberglass, and this was done in Australia. Another fiberglass in Australia. You may be wondering, why so much in Australia? There's a company down there that really loves FEVE, and they sell a lot of it. So they've been very generous with their projects to show and allow us to use. So thank you very much for that. Another application with the bright colors. And this is also a fiber cement application. So you can see here that bright red, and then that, design. It's actually a pattern there. So in closing, by now, hopefully, you can define FEVE coating technology, history, and unique weatherability properties, as well as its ease of application in the architectural market. Discuss the importance of the form of coatings, of course, what it looks like, color, finish, and gloss range. Hopefully, you have discovered the function of a fluoropolymer coating, and of course, that's the performance, depending on the different substrates and types that you're using, water-based, solvent, powder. And finally, describe the sustainability and environmental impact of a long life coating. Again, a long life coating lasts a long time, and so it eliminates repainting. And of course, we reviewed what goes into a painting process. So eliminating those processes is a benefit to the environment overall. So with that, I think I do have a few minutes for questions, and
Kristen,
I've got them right here.
We've got about 5
Go ahead.
minutes for questions or so, and I'll give you a chance to go through those. Thank you very much. Great presentation. I'm glad somebody in the world is handling chemistry for the rest of us. And I was thrilled to see so many projects that have won awards in magazines and I've seen around. So a lot of great representation in the stuff you showed. But take a moment to go through those. We've got about 5 minutes left, and we'll answer as many as you can get to. So thank you very much. Hold on with us.
All right. There's a question here about the curing temperature for powder coating. With FEVE, it's roughly 400 degrees Fahrenheit, 200 degrees C, but there's a range there. Again, we're the resin supplier, so the paint companies themselves, they optimize their powder coating and their line to cure it where they need, and then of course the job shop as well. So, but roughly around 400 degrees Fahrenheit. Someone asked about cool roof coatings and resistance to yellowing, and we do have information on that. We did a little study on cool roof coatings. It was with our water-based systems, and it was actually with blends of some of our water-based emulsions and different acrylic resins. And so I would really encourage you, when you get the email tomorrow, hopefully you'll have my contact information and you can reach out to me directly. If not, I believe I will have a list of these questions and I will be sure to email you directly with that specific information. I think I'm going to interpret this question, but if I'm wrong, hopefully we can resolve that. It says, how do these fluoropolymers perform compared to silicone? I would call that polysiloxane type coatings, but if you're talking about silicone adhesives or joint seal, I'm not going to speak to that. So if that's what your question was, I apologize. If it's compared to polysiloxane, more of a coating chemistry, then I will speak to that. Generally speaking, fluoropolymers, FEVE systems in particular, are going to weather longer than polysiloxane. Polysiloxanes do weather well, though, so just keep that in mind. And honestly, polyurethanes weather well. So it's not to say that they don't weather well. It's just to show that if you need something that's going to weather for decades, fluoropolymers are really what you need. But in general, with polysiloxane, there are advantages and disadvantages to each chemistry. FEVE systems oftentimes utilize isocyanate. And for a 2K system, polysiloxanes don't need that, so advantage for polysiloxane. But as far as application environment and how you cure it, FEVE systems, just like urethane systems, tend to have a little more flexibility in their application window because they don't rely on moisture to cure, and a lot of polysiloxane systems do. So you could have some variability on a job site, and you have to be very careful about that. There's also some differences in impact resistance and adhesion over time. We actually have a little presentation on that as well. So if you reach out to me directly, if I'm answering your question properly, then I'll send that to you. And if not, I'll be sure to follow up once I get this list of questions. And so I think I'll see if there's one more here that I have enough time. Any information on FEVE's chemical resistance to strong acid and oxidizing chemicals at elevated temperatures? Elevated temperatures, I'm not so sure about. A lot of what we do is at room temperature. I actually myself, when I was working in the lab, did a study with 98% concentrated sulfuric acid, which was a little bit intimidating, but I was able to do it. And we were able to resist that acid for several hours. That was really the standard because, sulfuric acid is pretty intense. But if you do a lower concentration, I've seen good resistance with FEVE systems to that, hydrochloric acid as well. Again, we have this information in kind of a little document, a little technical bulletin that I'm happy to share with you as well. So if you want to reach out to me directly, if not, let me know. And there was a final question on how to call me. So just, Paul, just to be sure, in that email that you send out, will my contact information be on that?
Kristen, I just, through the chat function, sent your email address to the entire audience. So you're going to be bombarded.
Oh, perfect. Okay. Okay. Well, I think we don't want to take everybody's time too long today, so I will wrap it up there. But any questions I did not get to, I'm happy to follow up with you. And again, please feel free to reach out. Appreciate everybody's attention, and I hope it was informative.
Thanks very much, Kristen. And just to reassure everybody that the questions, Kristen is going to get a list of all the questions that were submitted that she didn't get a chance to respond to, and you have her contact information. Great presentation. Thank you so much. For folks who want more information, you can go to lumiflonusa.com. And a reminder that the credits and certificates are going to be handled automatically, and you should allow 7 to 10 business days for them to process. The recording of this webinar will be posted on the metalarchitecture.com website by Monday. So you can review that there if you want. Thanks everyone for attending. We're doing another webinar on February 18th on designing with architectural insulated metal panels. And for the most recent and updated list of webinars, go to metalarchitecture.com. Thanks for attending. Hope to see everybody in February. And Kristen, thank you very much. What a great presentation. Really appreciate it.
Thank you.
Bye, everybody.